Now we're going to talk about the concept of magnetic flux, and the symbol for magnetic flux is phi with a little m, or I say phi, so don't be surprised if I say that, but physicists will say phi. Okay, so this is a symbol for magnetic flux, and conceptually what magnetic flux is you can think of it as like the number of field lines crossing through a given area. And so in magnitude, the flux is BA cosine theta. Now, it's not a vector, so I said magnitude, but it's just that. And so what that means, if you think about it, and if you think about it conceptually, so here I have an area, and so some given area, and I have some field lines. I'll have them coming out of it, some field lines coming out of it, and here I have them perpendicular. So this has some flux to it, and then if I have another area like this, that's supposed to be the same area, this has more flux. Now, the cosine theta has to do with, you would say, the angle is the normal or the perpendicular to the area. So if I have, okay, so imagine this going into the page. I'm going to have maximum flux when our electric field is perpendicular to that area, because the direction of the area, because really we're saying the B is a vector and A is a vector, and we're taking something called the dot product. And we need, so if area is a vector, how can area be a vector? Well, area has, as a vector, area has the magnitude of the area and the direction of the perpendicular. So you have maximum flux when the field lines are perpendicular. So when the field lines are at a slight angle, you're going to have less of a flux. So you have more flux if you have a stronger field, a bigger area, or an angle closest to 90 degrees where it's coming straight through. Now, the reason this is important is not so much because of the flux, but because of a change in flux. When flux changes, there's something called Lenz's law, and it's, if we have a wire, then the change in flux is going to induce a current in a wire. So we saw how a current creates a magnetic field. Well, a changing magnetic field induces a current. If the magnetic field is not changing, then there's no current. So for instance, if I have this circle, here's a wire, and I have a magnetic field going into the page, and nothing is changing, the area inside the wire is not changing, the magnetic field is not changing, the angle is not changing, there's no current. But when I start changing stuff, I'm going to induce an electric field, and so I'm going to induce a current in this wire. And the way you figure out the direction of the current is the direction of the current is going to oppose the change in the magnetic field. The wire doesn't like the change in the magnetic field. It's very conservative and says, no, I want things the way they were before. And so it's going to create a current that's going to oppose the change in the magnetic field. So we're going to have yet a new type of right-hand rule. And here's our new type of right-hand rule. If I have a current loop, so here I have a current, and my current is moving in this direction, and I want to figure out what direction the magnetic field is from this loop. You can use what you've done before with currents in the magnetic field, but a quick way to do it if you have a current loop, is you just curl your fingers in the direction of the current, and the magnetic field is in the direction of your thumb. So if I have a current carrying loop, it makes a magnetic field in the direction of your thumb. So this one, the magnetic field is coming out of the page, and if I have a current carrying loop this direction, the magnetic field is into the page. So let's go back and look at this example. So here I have a magnetic field going into the page, and let's say I decrease that magnetic field. I start decreasing it. So it's changing. And I'm only going to induce a current while it's changing. Once it stops changing, there's no current at all. So I decrease the magnetic field. So if I decrease the magnetic field, what's happening to the flux through this loop? Is it going up or going down? It's going down. So you're going to induce a current to oppose that. It's going to want to add to the magnetic field. So in what direction would a current go to make the magnetic field increase in the direction that it's going right now? We want to make a magnetic field into the page. And so what direction is our current going to be? If we need to have this current make a magnetic field into the page.
The current goes clockwise.
The current is going to go clockwise, because if the current goes clockwise, it makes a magnetic field into the page, and that opposes the change in the magnetic field. Because the magnetic field is decreasing, so this is going to oppose that. Okay, so let's say this would be obvious, but if I increase the magnetic field, what direction would the current be? So the current is going to be counterclockwise. So let's look at some other examples. Okay, so here I have a magnetic field coming out of the page, and I'm going to increase it. So as it is increasing, we will induce a current in this wire, and the current we induce is going to oppose this. So what direction is the current going to move in?
Clockwise.
Okay, so why are we saying what direction? I see Connor says clockwise. Y'all are pointing your thumbs. And so we know if we're increasing it, we need to create a magnetic field into the page, correct? Mm-hmm. And so that means we need to have a clockwise current.
This Oh, well, I'm using the board, so...
Okay, so here, this is a wire, and this is a movable rod right here. I can move this rod, and we have a magnetic field. So our loop is this part right here. So as I move the rod in this direction, in what direction is the current going to flow in this loop? So let's think, as I move the rod in this direction, in what direction is the flux, I don't know, I'm not asking this right. How is the flux changing as I move the rod in this direction? In what direction? So we're having more magnetic field going into the page. So in what direction is the current going to go?
Wait,
counterclockwise.
Counterclockwise, because we need to make magnetic field coming out of the page, so we will induce it counterclockwise. So this actually leads to one of our other formulas, that if we're inducing a current, then we also are producing an EMF. And the magnitude of the EMF that we're producing in this particular example, the only one you have to know for physics B is what goes with this particular example, and it is that the EMF produced is B LV. And let's think about that and see why that might be true. We know that flux is basically BA. It's BA cosine theta. And we know that the change in flux is what produces our EMF. So change in flux, I can't seem to draw over there, so I'll do it over here. I can't seem to draw over there either. So our change in flux over time, is what's producing our EMF. Okay, so either thing can change to change the flux. Either the magnetic field can change or the area can change. As we're moving this wire of length L, what we're changing is the area. Now the area is the length of this wire times some number there. But if we think about, we don't need to know the actual area, we just need to know the change in area. And so length is a meter, velocity is a meter per second. And so the velocity is telling us, the velocity times the length of the meter is telling us how, that's a times, is telling us how the area is changing with respect to time. And so that's where this formula comes from. So if I want to find the EMF that's produced by the movement of this wire, that's what we get. Now this, I introduced this right here, which goes along with another formula, that the induced EMF so I wrote it up there before I actually introduced it. The induced EMF, and what is EMF measured in? It's volts. It's volts. It's what creates a potential difference, and creating a potential difference is what's going to make our current flow, equals, and the negative comes from saying it opposes the change in the magnetic field. N is the number of loops. So far in our example, we've only had one loop. The EMF is negative N times the change in flux over the change in time. So that's the EMF that's produced. Once you have that, you can use things like Ohm's law, because you can say your EMF is your potential difference, V equals IR, and you can work from there.